Okay, it should be recording now. Now, straight off, you should download some files that I've added to the Chapter 10 and the Chapter 11 notes. And if you actually download it, for example, if you download Chapter 10, it's now a zip file and probably goes to the Downloads folder. And so you can double click on it. And I've actually put a lot more material in that. Besides the .rnw file that we're using, I actually have a .rnd which creates a PDF slideshow. And of course this has all the data sets. So you can just access them the way we do in class. The same thing is true. You should also click and download Chapter 11. And I have some additions in both, well, mainly 10, but also to some extent 11. So if you want to follow along using RStudio, then you should download. Now I'm going to go into RStudio. Now go up to full screen. And so we'll go to Stat 512, and in particular we'll look initially at Chapter 10. And open the .rmd file, and I'm going to create a PDF from it. I wanted to say just a couple more things about multiple comparisons. And in particular, when we did, let's see, when we talked about multiple comparison, the main thing the book talks about are what I would call classical techniques. Fish's LSD, and then what are called spanning type procedures, in particular Student-Newman-Coles and Tukey's HSD. So I wanted to point out one other thing. A lot of the modern procedures we can do with the pairwise.t.test. And in particular, I wanted to show you one additional thing. When you do this code and you specify a just none, then this is equivalent to doing Fish's LSD because the p-values are not adjusted. But I did one thing that was different in the code. I actually saved the output to an R object called LSD. And from that object, I can actually extract the p-values. Now this becomes important to have access to the p-values if in fact you want to change how you display the output so you can see where the differences are. So if I have those outputs, for example, I could stretch them out into a vector, and from that vector, then I could have various, by a little bit of coding, I could have various ways of representing what the mean differences are. You can see what they are, of course, by looking at the ones that are less than 0.05, A versus C, and these are the four models of sols, A versus C, and C versus D are both significantly different at the 0.05 level. This is using an unadjusted p-value method. And I want to talk just a few minutes today about how you might adjust those p-values and how that relates to what we did in the last section dealing with other types of multiple testing procedures. But before I do that, I just want to mention about the Student-Newman-Coles and the Tukey significant difference because they're both based upon the concept of a span. And in order to do that, let's see, I want to slide it this way. And so I'm going to go back here and I'm going to start up the software that allows me to project up, the reflector software. And so I can now display it, and I will bring up some notes. And I just wanted to point out one thing to you. Oops, why did I change here? So if you take a look at this, at the methods, if we have a set of means, y bar 1, y bar 2, up to y bar sub a, if we have these means, what we need to do is rank them. And usually what people do when they rank them is they'll call them like y bar, and then they'll put a bracket around the 1, and that means it's less than or equal to, let's see, what is it? Less than or equal to y bar. Not sure why this is acting up. There's some stuff on there. Y bar is 2 less than or equal to, and so forth, up to y bar sub a. But notice the brackets, I mean they're ordered. So when we do the spanning type procedures like Student-Newman-Coles, we actually look at how far apart they are. That would be a span of 2, and this would be a span of a. Now what happens is the actual Q value you use for rejection gets bigger as the span gets bigger. And so Student-Newman-Coles takes account, if you're comparing the smallest to the second smallest, it's a span of 2. The smallest to the third smallest, it's a span of 3. Now what Tukey does is he has a span of A for everything. That's a bigger value, it makes it harder to reject, and that's why his is more conservative than Student-Newman-Coles. So this is sort of the idea behind them, and why you'll find that Student-Newman-Coles is sort of between Fish's LSD and Tukey's. And as I've mentioned to you, the procedure with Chaffee's is even more conservative. But it does let you sort of poke around and do about any contrast you're interested in. Now the point is, right now, if you look at what's built into R, there's a procedures for Tukey's HSD, but not for the Student-Newman-Coles. But the fact is that you can compute what are called the Q statistics in R, and you can get corresponding probability values or quantiles, and that actually lets you, with a small amount of code, develop code to do Student-Newman-Coles. We could actually do the adjusted p-values also, just as you can do for Tukey's. So that's one of the advantages of R, that if it's not built in this case, it would probably take maybe 5 to 10 lines of code to do it. Now I want to go down to, I want to talk just a little bit more about this last section. And so we were talking, this table in particular was the key thing, and I just wanted to point out one thing to you. Because with these procedures, we're not talking about the ranked means, we're talking about the ranked p-values for most of the procedures. So if I look at this particular table, V is kind of the key statistic. It's the number of false positives, or the type 1 errors. And then the other thing that you might want to be concerned about is T, which is the number of false negatives. But most of the focus for the controlling the error rates when you're doing many-test is related to controlling V in some sense. And so if you look at the probability V is greater than or equal to 1, which is the probability you make at least one false positive, that, if we can control that at the O5 level, that's what we call the family-wise error rate. And that's equal to 1 minus v equals 0. And I just wanted to point out one thing that I may not have emphasized enough. If you go back and look at this particular calculation, where did that come from? In this case, we're talking about a situation where we have m tests. And if we're doing pairwise comparisons, and in the case that we're doing, we have m equals 6 because we have 4 treatment levels, and if we're comparing all pairs of those, we have 4 things taken 2 at a time, which is 4 times 3 over 2, or 6. So we have 6 comparisons when we have 4 treatments, and the question is, what happens if, where did we get this from? In other words, what's the 0.95 to the m? Where did that come from? Well, it actually comes from the idea that if we have hypotheses h1, h2, up to h sub m, what we're doing is we're looking at the probability that we get at least one false positive. But the way we compute that, instead of v greater than or equal to 1, we typically compute this as 1 minus the probability of v equals 0. And that means we have no false positives, which means if the null hypothesis is true, we accept everything. So if we look at the probability of h1 and h2 and so forth to hm, then what is that? Well, that's what we were computing there. In order for this to be the product of the probabilities, what do we need to have? We need to have independence of the hypotheses. So I can write this as a product from I equals 1 up to m of the probability of h sub I. And if they're all 0.95, accepting an all when you should, then it's just 0.95 to the nth power. So that's where that comes from. So in other words, if I look at this, that's where it came from. So if I'm looking at Bonferroni, and if I'm looking at a lot of these procedures, they assume independence of my null hypotheses. But there's a problem with this. And the problem is that if I'm testing the first group versus the second, the first versus the third, both of those involve the first group. So it's not likely they're going to be independent. So at any rate, just to indicate, and one of the things I didn't tell you is how do you get these adjusted p-values? How did we get the adjusted p-values for the Bonferroni? Well, it's quite simple. Do you remember the statistic, what I called the LSD that I saved previously? That LSD, if I used $1, that extracts the p-values from it. Now suppose I multiply it times m, which is the number of hypotheses I'm testing, in this case 6. So if I have 6 times this, these are the LSD p-values, this is what I get. Now compare what I get from the output of using the pairwise t-test with Bonferroni to this, and what's the difference? All the ones that are 1 or less are the same. So the way we work this is that we simply set anything greater than 1 back to 1. And that's how you get the upper table. Now, what about these other adjustments? I'm just going to indicate briefly how those go. And I put a link in here to actually the SAS documentation. They have a procedure called proc-mult test, which does these types of things. And you can see that the Bonferroni, they're using R, capital R, as a number of tests. So they're simply saying R times the p-values, and if it exceeds 1, set it to 1. So we could actually write some R code to reproduce that matrix you see for the adjusted p-values. But what about these other procedures, such as what we call the step-down procedures? And here's a step-down procedure. And this depends upon, if I look at the p-values, and I have m of them, and suppose I rank them, so I have p1 is less than or equal to p2, less than or equal to p2, less than or equal, and so forth. Got to get my hand off of that. P sub m. If I rank the p-values, oh, I'm sorry, I didn't go over here. If I rank the p-values, then the procedures that I talked about, these are the p-values, but they're ranked. So in this case, they say, suppose these are the rankings. They didn't use the brackets. But I'd rather use the brackets because it's a more common notation, actually. What it does is it multiplies the smallest one by R, but then as it gets bigger, for the second one, it multiplies by R minus 1, for the third one, R minus 2. In our case, it would be m minus 1, m minus 2, and so forth. But it also, when I'm looking at S1 stands for the step-down p-value. For the second one, it's either R minus 1, or in our case, m minus 1 times the second smallest, or the S1, which is the p-value in the first step. It's the max of those two. And then at the next step, it's m minus 2, or in their notation, R minus 2, times the third smallest p-value. And then, again, you look at S2, which is from the second step, and so forth. So in other words, that's more conservative because in the Bonferroni, you're multiplying everything by R. So the p-values, it gets very hard for p-values to be less than 0.05 if you're multiplying them by R. Okay? So as, you know, if you have small p-values and if it's significant enough, it still gets multiplied by R. Now there are some other procedures. SIDAC has an adjustment. Instead of using multiplying by R minus 1 and so forth, it actually takes 1 minus the smallest to the rth power. And this tends to be a little bit less conservative than the home procedure. This top one is the home procedure. Now it turns out that Hochberg showed that if in fact you start the other way, you start the maximum instead of the min, and you simply set the first one to the maximum p-value, and then the second one is the second largest, and you multiply it by 2, or again, it's that maximum p-value. And that's called a step-up procedure because you're starting in the max and working down instead of starting at the min and working up. It turns out that this is more powerful than Holmes' procedure. And it's in fact uniformly more powerful if in fact you have independence. Now, this was all well and good, and these were nice advances over certainly doing the Bonferroni, and they provided better protection than, say, Fisher's LSD, which didn't, you know, that the actual family-wise error rate could be quite high for Fisher's LSD. So if you go on to the false discovery rate, and this came about for people that had a lot of these tests, if M is big, then the false discovery rate came into play, and that particularly was important in genomics where you may have n very big. And those are the adjusted p-values for it. Now, the problem with initially, this initial procedure assumed independence again. And if you have n very large, that might be reasonable to do. But the second procedure that I talked about, was this BY procedure as opposed to the BH. And the BY procedure allowed you to have some type of dependence, which is probably more realistic. So what is the end result here? You've got all these methods, and there are others. But I wanted to give you a flavor of this, and R does this very nicely. What are the other things we can look at? Or what should we be considering? Well, first of all, of course, for any given test, you can do several of these, but it really depends on several factors. Generally speaking, these false discovery rates do not protect you as the false discovery rate does not protect you as much as the family-wise error rate. In other words, there's no guarantee if you control the false discovery rate that you have reasonably controlled your family-wise error rate. I mean, they're more liberal tests, and so they reject more often. So it's sort of up to you. If you want to be a bit more conservative and not so conservative as the Bonferroni or as liberal as Fisher's LSD, there are these intermediate procedures that you can use. So there's a fair amount to say for the Hochberg procedure, and there's also a fair amount to say for the BY procedure, depending on the level of protection you want. Unfortunately, that's going to be up to you. But in particular, if you have a lot of tests, like in genomic studies, then I recommend you do the last one. In other words, I recommend you use false discovery if you have a lot of multiple comparisons. I should mention one final fact. These multiple comparisons procedures do not necessarily assume that these are pairwise tests. They can be any M test. But if the M tests are too highly correlated, then you get into trouble. So again, that initial procedure I showed you assumed that you had independence. Now, there are various papers out in the literature that discuss this issue in more depth, so I just wanted to point out the problem to you. But if you're doing a PhD dissertation or something and you come across and you need these procedures, then I would recommend that you delve into it a bit. So are there any questions on this? Because this is what I wanted to talk about in Chapter 10. Okay. So now, before we go into Chapter 11, I wanted to talk about two things. One is Assignment 9, and the other, and I'll actually be posting 10 before long for those of you that work ahead. There are two things I need to discuss. When is Chapter 9 due, and when is the exam? When is the midterm? And I have two classes, and since some of you are taking both classes, I don't want to do it the same day. So I was thinking about having one of them the day after the break, the fall break, which I think is the 16th. Is that right? We just get the Monday and Tuesday off, right? We don't get Wednesday. So I'm thinking about Wednesday for one class and the following Monday for the other. You're first. Do you have any preference?
Yeah, we have 5:51. The first week after the.
Is it a Monday?
I think
Is it toward Tuesday and Thursday?
first week after the.
It'd be the day after Tuesday.
Yeah.
Like if we had it Monday, we'd have another exam Tuesday for 51.
But that's going to happen. Yeah.
I just prefer the 21st just because the 15th I have a manuscript due and so I'm kind of focused on that.
Okay. The 21st is the following Monday.
Yes.
Okay, we'll go on the 21st the following Monday. However, I'm going to make the assignment 9 do that Friday before the exam. Now, I'm going to go ahead and give you 10, so I recommend that, I'm going to give the assignment for 10 pretty soon. We've finished it now. And so I would recommend that you start working 10 prior to the exam, just to get the experience of doing it. And the exam will probably at least cover up through chapter 11. Because 11 is a pretty short chapter, it's not going to take us too long. And maybe into the beginning of it. I'll let you know how far. Since we're doing it 21st, I'll let you know how far we're going to go. Yes.
Can we get the feedback of the first assignment?
Yeah, I actually have a grader, and she'll be grading that hopefully this weekend.
So we will have the right answers for all the first assignment.
Well, she'll grade. I'm not saying that I'm going to give you the answer sheet, but she'll grade your homework, and I'll have her make comments about what she did. And I can answer, once she's graded and you get it back, we can take questions in class. So the exam will be the 21st, and I'll need to make arrangements. There's a distance-based component to this, and I'll make arrangement with the distance-based students as to how they'll take that exam.
Just for the exam, in terms of what needs to be done by hand or what we need to know in R, is it like 50-50 or how does that work out?
Well, I'm not going to have you do a lot of hand calculations, and you're not going to be sitting at the computer doing R either. I may ask you to interpret the R output, or I may ask you what is the R function to do such and such. But I'm not going to have you do a lot of. I'm not saying I won't have short calculations, but it will be short. So you might want to bring a calculator. Does anyone have calculators anymore? I still have these old HP reverse Polish notation calculators, which I think, what?
I love those.
Yeah, I like them. They still keep working, after 20 years. Or maybe longer, I don't know. It's been a long time. At any rate, so I'll probably have I'll post the due date, but the Chapter 9 will be due the Friday before the exam, and then that following Monday will be the exam. Okay. So let me take a look. Let me take a look at Chapter 11. I'll set that as the working directory. So in Chapter 10, we looked at the case where we had a model y sub ij equals mu plus alpha sub I plus epsilon sub ij. The only thing that was random was the epsilons. The alpha sub i's were fixed. By the constraint we imposed, the sum of the alpha sub I was equal to 0. But that's only one of many possible constraints, and as we have discussed, this is what jump does, but it's not what RSS do. RS sets alpha 1 equal to 0, and say I set the last term to 0. Now, OR allows you to do about anything, including setting the last one to 0, or it allows you to do the sum as 0, but you need a constraint. Now, you might wonder why. Why don't I just model it as y sub ij equals mu sub I plus epsilon sub ij, and there are a mu sub i's, and I can estimate all this straight out. You might say, well, why are you re-expressing, or what we call reparameterizing, as mu plus alpha sub I? Why are we doing it? Well, for the one-way analysis of variance, you really don't need to do it. You could just use mu sub I plus epsilon sub ij as your model. You could. And in that case, you would have what we call a design matrix that would have, the first column would have a 1 corresponding to group 1 and zeros every place else. The second column would have a 1 corresponding to group 2 and zeros every place else, and so forth. And you can see that actually, those columns are independent of one another. So y have a vector of 1s, which represents the mean, and then you have corresponding indicator variables, or in the case of the sum of the alpha sub i's for that last group, you've got -1s. Why do that? Well, the reason is when you get to the two-way analysis of variance, that whole strategy, when we have two groups now, and two factors, I didn't mean two groups, two factors, each of which has multiple groups, and we look at them in combination. When we have that type of model, we need to have the types of notation we're using now. The mu sub ij, where I represents the first factor and j represents the second factor, that doesn't let you look at interactions, for example, between factor A and factor B. So we're setting the stage of what we're going to need to do anyway once we get into chapter 12. So when we looked at the fixed effects model, there we assumed that the alphas were fixed. In fact, by the way we constrained them, in our case, it was the sum of the alpha sub I equals 0. We were testing that the mu's are equal, but that's equivalent to testing that the alpha sub i's are all equal and equal to 0. Now later on, we're going to show that we get a mean squared for error, and we get a mean square for A. That's an A. Well, it's not a very good A. And it turns out that the expected mean squared is sigma squared here. But the expected mean squared for A is equal to sigma squared plus n sigma squared sub A. In other words, when we have I didn't mean to do that. I meant to swipe on the computer, not the iPad. We can get what are called expected mean squares, and for both the model, the first one, which we call a fixed effects model, or we sometimes call it model 1, we're assuming the alphas are fixed, but suppose the alphas aren't fixed, suppose they're random. So suppose instead of having A fixed groups, I have a whole bunch of groups. Like I might have families. And I want to look at the family variation. There are a lot of families. So I sample A families at random out of this much larger group of families. Now I don't have A fixed groups. I have a random sample of groups. Well, suppose you have a certain section of a class at a large university. Maybe you have 25 instructors teaching the same thing. And you want to learn about instructor-to-instructor variability. Now, you may not be interested so much in those 25 specific instructors. You're interested in the instructor-to-instructor variability. And you can view those 25 as a random sample from some larger group of potential instructors. In that case, the A's, the alpha sub i's are random variables. So in the random effects model, we not only assume we have the same model, it looks the same, and by the way, these n's those could be n sub i's. In other words, the sample sizes in each group could vary. The book and I am writing it as equal sample sizes, but they don't have to be equal. So if in fact I have a random sample of these treatment effects, then the alphas are random variables, and I'm going to I'll assume that they have a mean of 0. If they're not, I could move the non-zero part over to mu. So it's not restrictive to make this assumption that the alpha sub i's have a mean of 0. And a variance of sigma squared sub a. So the variance, so think about it this way. I've got a group of individuals from, let's go back to the teacher example. Each teacher has a group of students, right? And you're measuring performance on the students. So I have two sources of variability here. I have the student-to-student variability, and I have the instructor variability. So the instructor-to-instructor variability is what the sigma squared sub a is. The student-to-student variability is what the sigma squared is. So I have two sources of variability. Now we also call these variance components. So in the agricultural sciences, this is very often types of models that you have to use. You have some, in fact, when we get to more than one factor, a lot of times some of our factors will be fixed and some will be random. And this is called a mixed model. And the mixed model is probably the most common type of model you have, more common than a completely fixed model or a completely random model. So, if you look at what Phil Turk does in the ag school, for example, the mixed models is probably his most common consulting situation. Now, it's also true that normality, which we're going to assume, may not hold. And so you can get into mixed models which need other assumptions other than normality, but we're going to assume normality in our case here in this intro course. He teaches a stat 645 where he gets into more assumptions. So in this case, this is the key thing. Instead of this alpha sub i's being fixed and the sum of alpha sub i's equals 0, that's by definition, then we're going to assume the alpha sub I are a random variable, and they have a mean of 0 and a variance of sigma squared sub a. So what I'm interested in, instead of testing that the alpha sub i's are all 0, I'm interested in the variance, sigma squared sub a is 0. That's what I'm interested in. Okay. Versus, of course, it's positive. Variance can't be negative, so the alternative is that it's positive. So if I look at the mean squares and take the expectation of the mean square, for the random effects model, this is what I get. But for the fixed effects model, when I get the expected value of the mean squared, it's still sigma squared. It's still sigma squared for the fixed effects model, but if I look at the expected value of the mean squared, it will be sigma squared plus n times the sum of the alpha sub I squared over n. This quantity right here is sort of like a variance. When you do the sum of the y sub I minus y bar squared over n minus 1, that n minus 1 is an adjustment to remove bias. Here, again, I have a minus 1 instead of n minus 1 because I'm doing this over a. So it's sort of like a variance term. So on the surface, these look quite similar. And in fact, the way we compute things are identically the same. So we have two types of models, the fixed effects model and the random effects model. Is everyone clear on that? If I write this part up here, they look the same. When I talk about the epsilons, they're the same for both models. The only difference is the alpha sub i's I now consider to be random effects, not fixed. Okay. So think about the example of teachers or instructors. I get a random sample out of some population, and then I measure, and they teach a group of students, and I measure the scores on the students. Maybe it's final overall course average, and maybe all the courses have the same types of. If you had a standard, like in let's take for example Math 126 here. They have a lot of instructors, and I believe all the tests they give are standardized across all sections. So if there are differences, those, of course, there could be other reasons for differences, right? It could be because of the time of day. It could be a Tuesday, Thursday is different than a Monday. Well, are those 3-hour courses? I forget. But at any rate, it could be because of the days of the week or the times of the days could cause differences. So it's not necessarily just to the instructor. So, but the point is that you have scores on a group of students within a group of instructors that you could view as a random sample. You may not be interested in those specific instructors. As a chair, what you may be interested in is whether there's a lot of variability from instructor to instructor. And if there is, that's a problem. So we test the sigma squared sub A equals 0. Now, let's talk about follow-up procedures for a minute. What is a follow-up procedure for a FEM models or fixed effects models? Well, we've been talking about that a lot. Typically multiple comparison procedures. Perhaps we're talking about orthogonal contrast. Perhaps we're just talking about estimating certain effects. But the point is we're considering the alphas fixed, we estimate them, and we make certain inferences about them, whether it's multiple comparisons or whatever it is. But I'm not interested for the FEM model, the RIM models, REM models. I'm not specifically interested in those specific alphas. I'm interested in the population of possible alphas. And in particular, I'd like to understand of the total variability, perhaps, how much of that variation is due to the instructor variability. So we can define, we talked about correlation R, right? R was the product moment correlation, or the Pearson correlation. We did that in chapter 9. And when we did a regression, we got a coefficient of determination, or an R squared. And R squared was the percent of variability of the regression model you explained by the predictor. You remember? So here we might ask, what is the percent of variation explained by the treatment effects? And we'll call that R sub I. And we call this actually the ICC, or the interclass correlation. That should be intra-class, not interclass. The intra-class correlation. It's the proportion of the total variance explained by the treatment differences, the among treatment differences. And so I'm going to denote this by R sub I. And if you look at the form over here, the last one, sigma hat sub A squared is the variability among the alphas, right? I have a hat on it to indicate I have to estimate, and I'll talk about that in a minute. I have a hat on it, meaning it's an estimate. Sigma squared sub A is a parameter. I have to figure out how to estimate it. And we typically indicate estimators by putting a hat on them. And then sigma squared sub T, T means total. It's the total variability. And that includes, if you look down here, the sigma squared sub T is sigma squared, it's sigma squared sub A plus sigma squared plus sigma squared sub A. It's the sum of those two variance components. So the sigma squared sub T is equal to sigma squared plus sigma squared sub A. I add those two variance components together. Now I have to estimate both. And obviously, if I'm going to estimate sigma squared without a subscript, what do you think I estimate it with? Well, if the expected value of the mean square is this, wouldn't it seem reasonable to use the mean square error to estimate it? If the expected value of the mean square error is sigma squared, right? So why not just use the mean square for error to estimate sigma squared without a subscript? And that's what we'll do. Now, if I were going to estimate sigma squared sub A, then it would seem that if I subtract out the sigma squared from this quantity, if I subtract this one out of this, I get n sigma squared sub A, and if I divide that by n, it would seem that is an estimate that I could use for sigma squared sub A. So if mean square error estimates this, and if I take MSA to estimate this, then it would seem that I could take the mean square for error and subtract off, the mean square for A, subtract off the mean square for E, and divide by n. So in a reasonable sense then, I could use sigma hat squared as the mean square for E, and then sigma hat squared sub A, I could take the mean square for A minus the mean square for E over n. Does that seem reasonable? It is, except for one minor thing. The mean square for error could be greater than the mean square for A. And you could get something negative, and then you're in trouble. Now, in practice, what happens is that if it's negative, you set it equal to 0. Basically, you're saying that variance component's very small. But there are ways, just like we had adjusted values for the p-values, we have ways of adjusting that get around this problem. And if you look at procedures in both R and SAS, you can do the n jump. In fact, you can make these adjustments, but get adjusted values. And I think that I'll do a little research on that and add some of that to the notes. But that's built into most software packages. So at any rate, by the way, this could also be written as 1 minus sigma squared hat over sigma hat squared sub t. And that's actually almost exactly the way we wrote the coefficient of determination when we did regression. If you look back at chapter 9. So on this line right here, I'm simply saying sigma hat squared is equal to mean square error. Sigma squared A is these differences over n. I just showed you that. And we can plug those in and get R sub I. Now, as long as we assume that if mean square for error is bigger than the mean square for A, and you get a negative value, as long as we assume that, we're going to set that equal to 0. That was sort of like in Bonferroni. If we had that adjusted p-value greater than 1, we set it to 1. It's certainly not going to be a correlation of it as a negative value. Well, it's not going to be a correlation in terms of variance components, at least. The Pearson product moment can be negative, of course, in regression. So, but the intraclass correlation cannot. It's between 0 and 1. Now, as I mentioned, the R squared, this is the way we did it in regression for the coefficient of determination. So it looks similar. But there's something to consider here. The coefficient of determination, or R squared, it was a measure of the strength of the relationship, but only the positive relationship between x and y. Whereas in this case, I'm not, in fact, we probably have nominal levels. That is, if we have levels of a factor, they're not even necessarily ordinal and increasing. They can be nominal. So I just have groups, and I don't have particular order for those groups. So obviously I can't talk about a positive or negative relationship in the sense that I can in regression. The interclass correlation coefficient is simply saying, is there a relationship between, them? And it doesn't matter whether or not it doesn't matter whether it's linear or not. In other words, it looks for more general types of relationships. And so it's a measure that we often use as a follow-up procedure, whereas, as I said, in the procedure for regression, we only had a measure of linear relationship. And you have to be careful with regression because you could have a strong relationship, but it may be nonlinear. And so you may come out to the conclusion that your R-squared, you may get an R-squared that's very low when in fact you have a strong relationship. That's because we're only looking at the linear relationship. So even in regression, you have to be careful that you don't have a nonlinear. And we had ways of sort of checking that out. Okay. So what are we interested in? What are we interested in? I'm going to come back to the R code in a little bit, but what are we interested in? We're typically, that should say hypotheses instead of expected mean squares twice. We're interested, to sort of summarize, if we're doing a fixed effects model, we're testing that the treatment effects are all zero, as treatment effects as defined by the alpha sub I. We're testing are all zero versus that they're not, there's some inequality. And then as a follow-up procedure, we typically use multiple comparisons of some sort, if in fact we reject null hypothesis. On the other hand, for RIM, we're testing that the sigma squared sub A is zero versus that it's greater than zero. And the expected mean squares, this is just a little table showing you the expected mean squares. And for the among, it's sigma squared plus n, sum of the alpha sub I squared over a minus 1. For the FIM and for the RIM, it is sigma squared plus n sigma squared sub A. Now, if you sort of think of this as kind of a variance, then there's not as much difference as you might think. But again, the way we make inferences is quite different. The within, that is, both have an expected value of sigma squared. So are there any questions on that? Those are two types of models. And what I want you to understand, we often call the random effects models the variance components model. So a lot of times in genetics, you're trying to figure out what the variance components are, for example. One of the idea that you have to sort of start thinking about is, what are my sources of variability? This is where a lot of people really mess up in their research, is that they don't understand the sources of variability and they don't understand how to control the sources of variability. Now, when you come to controlling the sources of variability, this is what we call the design of experiments. And Stat 513 gets into that. We'll get into it a little bit. 513 will get into in much more depth. And so if you're doing designed experiments as opposed to observational studies, then we need some way that we can control the variation. If it's too much variation, and let's call that noise, it drowns out the signal. And as a researcher, what are you looking for? You're looking for the signal. But the noise can drown out the signal. So if you design your experiment incorrectly, you may actually have something there, but you're never going to find it because of the noise. So it's just something to think about, and we'll be talking about that on several occasions. So let's go back, and I'm going to focus a little bit more on the FIM model, but in fact, a lot of what I'm going to do applies to both the FIM model and the RIM model. So here we have the model, and we're interested in, say, the error assumptions. But as I mentioned to you, we're also going to be interested in whether or not the random effects have. We make certain affections about the alpha sub i's too, and I'll talk about that in a little bit. So first of all, for normality, there are a couple of global approaches that we can use. We can either look at histograms of the residuals. In other words, we have A groups. A is number of groups. So in a saw example, we had 4 groups. So we've got A groups, and we could look at each one of those groups separately, or we could fit the model and look at the residuals. Now, usually it's better to fit the model and look at the residuals. A lot of times, we don't have that many observations in each group. And so if I try to do a histogram separately for each group, it's not very good because the sample size is too small for each group. So, but we could do side-by-side box plots, and those kind of work. We've done that before. We could also do normal probability plots on the residuals. So first of all, I'm going to go back now and look at the R code. Someplace. So there is a data set called brand. And what we have is light bulbs, and we have 4 different brands, and we're looking at how long each light bulb, no, 3 different brands, I'm sorry, how long each lasts in months. So we're looking at A, B, and C, 3 brands of light bulbs, and we'll look at the length of life of these 3 light bulbs. So I'm going to see if this fixes the problem. So I'm going to read in the data, and I'm going to attach it. And then I'm going to fit an LM. I'm going to do months tilde brand. That means I'm going to model months as a function of brand. Since brand is a factor, we're going to get a one-way analysis of variance. And then what I could do, if I look at fit Bob as dollar sign, this pulls out the residuals. Let's see if this, I've got to figure out what the problem is here. I keep forgetting to do it. There it is. That's what you would have gotten. So that's the histogram of the residuals, and you can see that it should be centered about 0. Here's the 0. And you can see that maybe it's skewed a little bit to the left. But the histograms are not the most effective way of doing this. It depends on the boundaries, and the histograms, as the sample size gets big, they're reasonable. But for small sample sizes, the histograms can jump around a lot, and it depends on where you cut the boundaries. Or it takes default cuts. In this case, we're potentially, we're looking at residuals, and in this case, it gives nice breaks, but again, it's perhaps not the best way to do it. So rather than do this, it might be better to look at box plots, and there must be some size I can set it to that they'll show up. At any rate, that was the box plot. You notice that it appears that brand B is the winner. So if you were sort of looking at that, you'd probably say, well, there's probably not a difference between A and C. It appears that B is larger. Now, if this were a fixed effects model, we would then, if we did an analysis of variance and we have a significant difference, then we could do these follow-up procedures. So it appears that there are some differences here. But perhaps most importantly, we can look at the normal probability plot, and that's not going to plot either. Let me just try this width parameter. Let me set it to 40. Well, no. This is actually for the width of, this is actually for the width of the output. I don't necessarily want to control that. So I'm going to go ahead and execute it, but it's not going to work. But that's it. Now you notice you're asking the question, is it linear or not? Those are the residuals. So there might be some things that you want to determine. It appears that it's somewhat linear, but it always appears as a group at the high end that not only that seems separated from the rest of them. And in this case, we actually might want to do some exploration as to which ones those are. Now this is where you could certainly label these graphs to indicate which ones are A's, which ones are B's, and which ones are C. It's possible to do that. In R, it's a little bit harder. If I show you, let me. I'm going to go in and mount this. Oh, I'm in the wrong place. I want to be here. Wait a minute. Oh, I want to be in chapter 11. Yeah. So if I were, I may have expired my jump license. Yes. This is what I hate about commercial software. We actually own it. I just have to upgrade it. So I was going to show you how you might do this in Jump. So I'll have to do that next time. I'll upgrade between now and next time. Okay. Sorry about that. And anyway, you might want to kind of know what this is, what these particular points are. And there is a way, of course, that you can do this in R. You can actually label the points according to their group. So you might be interested in those upper ones. It does appear that there's something a little bit tricky going on, but it's not totally clear what the reason it is. If I fit a robust straight line to that, it's going to be reasonably straight. But I would be interested to know whether those 5 observations are, like, for example, from group B. Okay. Now, another assumption we assume that if we have A groups, we're assuming that the variances are the same in each group. And there's a procedure in the book called the F max. So first of all, this by statement says, I want to compute the variances of months by brand. So the terminology is by months brand, by months brand var. Var says I want to compute the variance. If I wanted the means, I would simply replace var by mean. So it's going to compute the variances of months for each brand. And so if I do that, and I name them A, B, C just to be consistent, and then I print it out, you can see the variance of A, B, and C. You can see that A seems to have a lot more variability than B. certainly than B, and C has more variability than B also, but not as much as A. And you can sort of tell that from this box plot, that B has the least variability and A has the most. So the box plot sort of gives you that information. Now what the Fmax does, it takes the maximum variance and divides by the minimum. So in other words, it takes the ratio of the max, which is 6.116, and divides it by 2.663. And so we get a 2.297, and we compare that to a table in the back of the book. And I don't know if this Fmax, what we use for the quantiles for the Fmax, I don't know if we can compute that in R or not. I haven't looked at it, but I am going to show you another procedure we can do in R. So you get an Fmax of 27.7, and if you actually look at my code, well, if you look at, well, actually, you don't need to look at the code. The Fmax is 2.297, and yet I would actually have to have the ratio of the biggest to smallest to be 27.8. That's huge. In other words, if I look at it, it seems like my assumption of the equality of variance is a little bit questionable. And if I take the ratio of the largest to the smallest, the largest is about 3 times as great as the smallest. So you might think you'd reject, but you don't. And the reason is this test is not very powerful. It takes a huge difference in variances to reject. And then Bartlett's procedure is built into R, and I think I have, there's something called Bartlett's test, and I can simply compute this, and I do a Bartlett's test, and again I get a p-value of 0.8 roughly. So again, with Bartlett's test, you don't even come close to rejecting the null hypothesis. So in both cases, we're saying that assumption is okay. And maybe it's not too bad. It's not extreme. Not there. Here I want to look. It's not extreme if I look here, but the variability of the A to B is about 3 times. That is, A, the variance of it is about 3 times what it is for B. So in that sense, maybe I should be a little bit worried, but it doesn't reject. Okay. Now, there's another type of plot, the mean versus the variance plot. What we're going to do is compute. We've already gotten the variances. I computed the variances back here, right? Now let's compute the means. To compute the means right here, we do by month brand means, and so that gives us the means, and then I'm going to plot the means versus the variances. So notice that as the means gets larger, the variances get smaller. Now usually it's just the opposite. Usually it's just the opposite. Now if I'm looking at groups, and consider what happens when you have variance components. A lot of times you have the means increasing. The variance increasing as the mean gets bigger. And we're going to talk about transformations in just a little bit. But a lot of times you have exactly the opposite problem. That as the means get bigger, the variances get bigger. Okay. Now that could also be some indication that also could be true in a random effects model because of the sigma squared sub A term. So this is something that, something we may want to take a look at in terms of random effects models, and I'll come back to that point in a minute. Now, there are several other assumptions that we want to look at. We have an assumption of independence. There's one other assumption I didn't talk about, that I randomly sample two things. I presumably, in randomly sampling, not only say the instructors or the treatment levels, but I'm also randomly sampling the students within each teacher. Or I could put it another way, that the teachers get randomly assigned to the students. In other words, I want to have independence between those two variance components. That is to say, I want not only to have independence among students, but I want independence among instructors and between the students and the instructors. So if you, for example, if you had the best students going to this instructor and sort of a middle group going to some other instructors and the worst students going to another instructor, you don't have independence in that case. So you have to be careful that you have to be careful that types of things happening. That was some of the complaints about some of these test-based, with the Department of Education, some of the test-based strategies, that if you have inner city schools, you may in general have students that are weaker. And so for those schools to do well may be more difficult than in a rich suburb. So again, if you're looking at how you want to rate schools, you have to be careful about how you do it to be fair, because you're starting out perhaps with two very different types of groups of students, and certain schools are getting students that are in general weaker than other schools. And so that needs to be taken care of in any type of public policy. Okay, so now generally speaking, we're limited. We're limited in how we can test these assumptions. But one of the things we can see, that if the variance somehow depends upon the mean, then we may be violating an assumption for the random effects model. So this particular plot can also be used in the random effects model to determine whether or not you possibly may be violating the assumption. So there are some other types of plots that you might want to do. One of the things we did in regression is you plot the fitted values versus the residuals. And again, if you think about a horizontal line here, when you're doing the fitted values versus the residuals, you want the points, you want the residuals to be scattered about 0, up and down. So if in fact that's not the case, if they're predominantly above 0 for one group and below 0 for another group, there are various reasons where that could occur. But these are some diagnostics that I'd recommend that you do. They're not hard to do, as you can see. With a few lines of R code, you can easily check these assumptions. So, okay, what time are we getting to be? Okay. So we're actually going through this chapter fairly fast. I'm going to add a little more discussion about these diagnostics, and then we're going to talk about transformations in section 3. And I believe that's actually the end of this. So we're actually going to sort of cut through this chapter 11. There's not that much more in it. 10 was the much bigger chapter. So I'll spend next Monday finishing chapter 11. I'm going to add some more content to this, and so I'll probably update what's on the web. By the way, if you want to see how you create slideshows, then, so for example, if you look at, this is what I used to do, and it's much harder than R Markdown. And if I compile this, what it does is it creates a PDF file someplace. And it actually gives you a slideshow. It's just a PDF. This is the same thing, basically, as a PDF slideshow. So if you're interested in learning LaTeX or LaTeX, then you can look at the code here. This is what's called SWeave. I went from using RM Markdown, from using what are called RNO web files, .rnw files to .rmd, because the code for this is much more difficult. And so I wanted to use something. I didn't want you to get hung up on the LaTeX and not learn statistics. I wanted you to have something simple. And so that's why I sort of have moved away from this strategy, even though if I were doing a slideshow at a conference, I'd do it this way. Okay. So now I'm not going to be upgrading these. I'm going to be upgrading the .rmd files. Okay, any questions? Okay.